Hi everyone! In this video we are going to look at the concept of solubility. And solubility describes the amount of a substance, a solute, that can be dissolved in a solvent. And solubility is really important in biology. For example, a drug, if you're going to take it orally, must be water soluble. And then if its target is more nonpolar, it has to have some nonpolar character to it as well so that it will interact and bind favorably with the target. So we have to think about incorporating both polar and nonpolar components in order to have the water solubility as well as the nonpolar character necessary for drug action. So all this solubility is related to intermolecular forces. In order for something to dissolve and mix with another substance, it must interact favorably. So there must be strong intermolecular forces that can be formed. Take a look at these three vitamin structures: vitamin B6, vitamin A, and vitamin C. Two of these drugs, if taken in excess, will be excreted no problem through the urine. But one of these is fat soluble and can accumulate to toxic levels in your body. Can you identify which one of these molecular structures corresponds to the one that is most soluble in nonpolar fats? As you might be able to tell, the structures of vitamin B6 and vitamin C contain a lot of heteroatoms, that is non-carbon, non-hydrogen atoms like oxygen and nitrogen, that establish polarity in the molecule, creating polar bonds and therefore molecular dipole. Water is polar, so as you might imagine, these compounds are water soluble and can be excreted through the body. While vitamin A, on the other hand, only has that one OH group, so it has a high percentage of nonpolar character and is pretty hydrophobic. So it's going to prefer to mix with fat and be happier there because the intermolecular forces between the nonpolar fats and the nonpolar vitamin A molecule will be the greatest. Let's recap what happens on a molecular level when we mix a solute and a solvent. Remember that we have to break both the solute and solvent intermolecular forces and then form a solvent-solute interaction. And when that solvent-solute interaction is more favorable than the solute-solute or the solvent-solvent, that is when a solution will form favorably. And we can form solutions when this is not in our favor because of that entropy argument that we talked about before. Increasing the disorder in the system could cause a thermodynamically unfavored system to proceed spontaneously. By definition, solubility is the maximum amount of a substance in either grams or moles that dissolves in a volume of solvent under a set of conditions. So solubility depends on a couple things. It depends on the temperature. So as temperature increases, we increase solubility. We'll look at some plots of that shortly. And it also depends on the strength and type of intermolecular forces present between those solute and solvent molecules. You've probably heard of the idea that like dissolves like. That's the simple way of saying that polar molecules will dissolve in polar solvents and nonpolar molecules will dissolve in nonpolar solvents. We can see this idea of solubility play out when we look at the data associated with alcohols mixing with water and cyclohexane. So water is polar, as you are familiar with, and these alcohols have a polar component, an OH group, but as the alkyl chain increases in length, these become less and less water-like, more and more non-polar. So we see a trend in decreasing miscibility. And miscibility means that a solution is mixable. So if it's completely miscible, it can be mixed in all proportions. But there may be a solubility limit. So there may only be a certain amount that we can mix with water in order for it to be one solution. In cases where they are not miscible, they are known as immiscible, and you will see layers form. So as we get to something like octanol, it's not soluble to a significant extent in water, but a small amount will dissolve in that sample. So the London dispersion forces start to take over as the chains get longer, and they prefer to interact more with themselves rather than with water molecules. Now compare that to cyclohexane. Cyclohexane is a non-polar hydrocarbon, and so we might imagine that as we get longer alkyl chains here, those are going to be more soluble because we have a non-polar and a non-polar mixing. And as those chains get shorter now, we get less and less solubility because we're increasing the polar character. As the alcohol chain gets shorter, the hydrogen bonding contribution towards the total intermolecular forces becomes more significant because we have less London dispersion forces with the smaller molecules. So the hydrogen bonding with other molecules is going to be more favorable, causing them to be less miscible with hydrocarbon solvents like cyclohexane. I'd like you to take a look at these 4 compounds and see if you can rank them in order of increasing solubility in water. The solubility, as we said, is based on the intermolecular forces that can occur between water and the solute. So if water is going to interact with this hexane molecule, what kinds of intermolecular forces could be present between hexane and water? If you guess London dispersion force as the only force that could occur between hexane and water molecules, you'd be correct. There's no polarity associated with this, so there's no dipole-dipole and no hydrogen bonding that is possible. Looking at number 2, there are, of course, London dispersion forces, because those are present between all molecules, no matter what the structure is. But we also have this OH group. So we have dipole-dipole, and this OH could hydrogen bond with the water. So we have H bonding as well. This compound is a diol. There are 2 OH groups, so we have all of the same forces as listed above. And looking at compound 4, we have LDF, and this polar bond will attribute some dipole-dipole interactions there. So the molecules with the most favorable intermolecular force, the strongest intermolecular forces, are going to mix the best with water. So it looks to me like 2 and 3 have the most intermolecular forces that could exist between water and these compounds. So then we have to break the tie here. Which is going to have stronger intermolecular forces? They're both about the same size, 6 atoms in length, molecular weights plus or minus about 4 units, and dipole-dipole, hydrogen bonding. So the fact that this has 2 polar groups versus just 1 is going to make this a little bit more polar, and there'll be more hydrogen bonding, more dipole-dipole interactions. So this is going to be the most soluble with water, followed by 2, followed by 1, followed by 4 here, followed by 1 is the least soluble because it has the least favorable interactions. Water, with that strong hydrogen bonding network, is going to prefer to hydrogen bond with itself rather than to break those hydrogen bonds and let some of these hexane molecules in there. Thank you for watching this video. I hope you enjoyed it. Please let me know if you have any questions.